Oh boy, let me pause this and I'll re-plug it in here. Hang on a second. What's that? Nope. All right. You should not have had much trouble with the assignment on Thursday. If you're still cranking out on it, that you'll be fine. Like just get it done. It's those are all just real simple, quick water cycle problems. They don't take very long. So the assignment, the equations get a little tougher today. But in order to be able to do the equations, we first have to learn a skill. I, at one point in my career, dedicated a day or two to expanding and condensing logs. I went ahead this year and just decided, let's just throw it in, act like it's not a big deal. Usually, if you act like something's not a big deal, then it's not that big a deal. So I'm going to show you how to condense two logarithms into one. And then I'm going to show you one other little trick. And then we're going to head into our assignment. We're going to wind up doing quite a good portion of your homework assignment together. And I'm okay with that. So just kind of part of our we're going to have notes, and then part of the daily work that we will do interacting will actually be homework, which will still kind of feel like notes because we're learning stuff. But I figured let's learn it in the context of getting some problems done. So if that made any sense at all. So anyhow, first I want to show you how to condense a couple of logs together, and there's just some basic properties for this. So say you had like the log of, I don't know, x, and you added to it the log of y. You can go the other way, by the way. I'm telling the other class this. I'm not entirely sure that I have any real reason to want to teach you how to expand logarithms back. It's basically the backwards of what I'm going to show you today. So if it's in the standards, I'll show it to you. I probably will anyways, but I'm not going to make a thing. But this is super important, your ability to condense two logs. So anyone want to take, I was really impressed, like, and I don't even know if impressed is the right word. Like someone earlier just knew what this was, or they made a really good guess. Anyone want to guess what log of x plus log of y equals? Yes, that's twice in one day. You guys are kind of freaking me out. Yes, if you have two logarithms with an addition sign in between them, provided that the logs have the same base, which these, of course, are both base 10. If the logs have the same base, then you can condense them into one log. And notice that the argument of the log is a multiplication problem that was created by multiplying the individual arguments of the logs before we condensed. Yeah, the solving part of it isn't part of this yet, but eventually, yes, we're going to need to turn two logs into one, and then we'll apply that to what we learned on Thursday about how to solve equations. So for this portion of the lesson, we're really not solving anything. We're just putting two logs together to make one. Easy. And as you might guess, if we go change it up a little bit and we turn that addition sign into a subtraction sign, you can also condense two logarithms that are being subtracted by each other. What do you want to think this one is? Nope. Try to make a connection here that it wouldn't. No. Think about relationships. Like you hang out in math classrooms for enough years and you start to just feel like plus and times are kind of like really close kinfolk, aren't they? Yes. And so, in the same way that plus sort of condensed into times, minus is going to condense into his homie, which is division. So, when we condense a subtraction of two logs into a single log, the argument of the condensed log is a division problem created by the original arguments. That's a pretty easy association, I think, to make. I think, like, by this point in your math career, you've pretty well already developed that instinct that plus and times kind of go together and minus and divide kind of go together. I mean, that's not really an accurate thing to say, but it's the same kind of idea. So, so in a nutshell, when you condense a sum of logs, so a sum of logs becomes the log of the product, a difference of logs becomes the log of the quotient. So that's going to be a very important piece of information for you to have right there. Now, let's head in and start just looking at some examples of how to condense logs. So let's say I had the log of 4 plus the log of x minus 2. By the way, I'm leaving the bases off the logs right now. I need to stop that, but right now they're all just base 10, right? Bless you. And all of this stuff that we're talking about applies provided that the bases of the logs are the same. If they're not, that's a conversation for another day when we have to use a base change formula, which we're not going to talk about anytime soon. So for now, we have a log of 4 plus a log of x minus 2. We want to condense into a single log. What would it be? Could you clean that up for me a little bit? I was really hoping you would just say log of 4x minus 8, like that. So let's talk about how did that come to exist? Well, as we learned a few minutes ago, the addition of two logs condenses into multiplying their arguments together. And if you take this argument, the yellow one, and you multiply it by this one, the green one, you just have to do some basic distribution there because it's multiplication, right? So if you do multiply the 4 through, you get 4x minus 8. And that's that. Simple condensing. All right, let's go again. Log base 12 of 4x plus log base 12 of x plus 2. The 12 is not there to have any mathematical significance. I just, like I said a minute ago or so, I thought I should probably start throwing in some different bases. It's provided that the bases are the same, then everything is fine. So what are we going to do with the arguments of the logs? We're going to multiply them. Very good answer. Because the original problem is an addition, we'll condense or squish into one with a multiplication argument. And so again, I would encourage you to just go ahead and probably work this one out. Like, no need to show work here. So this is going to be log base 12 of what? 4x squared plus 8x. Very good. Nothing to it, right? Okay, how about this one? How about the natural log of 10 minus the natural log of 7x? Have you noticed that I always put parentheses around my arguments when the argument consists of more than one piece? Whether that piece is plus, minus, times, divide. If the argument contains any more than just a number or a variable, then I'm going to parenthesize it. So it's a good habit. What's this one going to be? Absolutely. You could just kind of sit and do 100 of these, not that we're going to, but you just start to really feel the repetitive sort of nature of, okay, so let me get this straight. Two logs with the same base. I got a log base E and I got a log base E, and there's a minus sign in between them. And as I know from a few minutes back, the minus is going to condense into divide. So Cooper just says, well, I'll just put this one on top, this one on bottom. See ya. Done. Nothing to it. Okay. How about this one? How about log base 4 of 6x squared minus log base 4 of 3x. First off, what mathematical operation are we going to use when we condense? Division for sure. Good job, guys. Minus condenses to divide. So I'm going to condense it into a log with a base of 4. And what's the argument going to be? It would just be 2x, right? So let's take a quick peek at why that happened in case you were a little, it does reduce, right? So it started out as first argument divided by second argument. And yeah, we just reduce the heck out of that thing. Cancel out one of the x's, the 6 and the 3 reduce. Piece of cake. I think I've only got one more, and then we'll head into what we're actually doing. So this is a necessary skill to do what we're doing today. And we'd have to use the base change formula, which we're not going to talk about for a while. I sometimes for a whole ever in a position to be working with logs, you'll be in the next math class, which is called advanced math or pre-calculus. And Mrs. Eklund will talk to you about the base change formula. So if you want to learn it, I'll show you. It's pretty slick and easy, but we generally don't do it in algebra 2. What's this going to be? We know it's going to be a log with a base of 6. Any thoughts? Yep. No. How about this? Yes. But there's a plus 3x in the middle. Lest we forget that when you multiply, bless you, when you multiply these two red things together, it is not as easy as just multiplying the x's and the numbers. Remember, it's a full 4-step process. X minus 4 times x plus 7. Yeah, you got the x squared. You got the minus 28, bless you. But don't forget that there's a minus 4x and a plus 7x that we have to consider as well. So that is the art of condensing logarithms together. If it's you're allergic to logs. Yeah, that's that. Plus condenses to times, minus condenses to divide. Any questions about that procedurally, sort of how to do that? Okay, there's one last thing I want to show you, and then I'll hand out the worksheet, and we will just spend basically the vast majority of the rest of the hour just doing problems together. I know second hour we finished problems 1 through 6, so we'll see. I want to do at least that much. And maybe if we get 1 through 6 done and you guys feel like you get it, then I can just kind of step out of the way and let you keep working. So let us get to it. You all right there, son? Tis the season, eh? Some people are pretty mathy and they look right at this and they already just know the answer. But this is a trick that I haven't shown you yet. You'll hear me say this a lot, and it sounds kind of silly, but we're going to drop the logs from both sides. So what happens is in an equation like this, if you think about it logically, what it's saying, remember, in this will at some point in your life make sense or not. Remember that logarithms are really just exponents. And so if you think about the left side is saying some power of 4 equals x minus 12, and the right side says some power of 4 equals 10. The bottom line then is when we think of these as logarithms, that the fact of the matter is that this yellow thing has to equal this yellow thing. We call that, math people may not all say it, but I just say we're dropping the logs. If the left side is a logarithm and the right side is a corresponding, like a similar logarithm, same basis, you can ignore them and just take the arguments and set them equal to each other. So in a case like this, x minus 12 logically has to equal 10. And that will make sense to you when you're darn good and ready. But in the meantime, what you need to know mechanically is that when the logs are the same on the left and the right, provided that you have a single logarithm on the left and a single logarithm on the right, then you can drop the logs and solve the resulting equation. And the resulting equations sometimes will pop out like this, a little sixth grade guy, and sometimes it'll pop out like a 10th or 11th grade guy. It really just depends on the situation. But in a case like this, you're like, oh, okay, I think I'm done, right? So that's how easy that can be when you drop the logs from each side. How about our instinct should be that we want to do the water cycle. And I guess what I'm trying to tell you in these few minutes of the lesson is that the water cycle isn't always what's appropriate. It's not always proper to do the this to the this equals this. Like that's really just not where you want to go. It actually still works. It's just really confusing to show you why. So just remember, if the left side is a log and the right side is a log and the bases are the same, as far as we're concerned, the logs can just go bye-bye. And we're left with this statement. I hope I haven't lost you with that. That should be a very simple concept. You just drop the logs and then solve the resulting equation. So this is more an example when I said that not all equations that pop out are little kitty equations, right? Like this is more a high school level equation, right? So it's a quadratic, and what do our instincts or our practice tell us that we should do with quadratics? We should always set quadratics equal to 0, right? So we've kind of left the land of logarithms now, and we're back to something that we did a lot of earlier in the year, and that is, okay, let's leave x squared and minus x, and let's bring the 72 over and set it equal to 0 like this, right? And then we have to do that f word, right? We have to factor. And so what does this quadratic factor down into? Tell me about my signs. Yeah, it's unavoidable that one's positive and one's negative because they multiply to make a negative. And then what numbers multiply to make negative 72, but essentially add to make negative 1? Positive 8 and negative 9. So that's, you've done that, I can say literally hundreds of times in my presence, factoring a quadratic trinomial. And at this point, we go back and rely on the logic of, hey, if this red thing times this purple thing equals 0, of course, then one or both of them have to equal 0. So what makes the red thing equal 0? Negative 8. And what makes the purple thing equal 0? Positive 9. So the last thing before I hand out the worksheet is this, and it's incumbent upon us now to start checking our answers, because starting today, you are going to start getting extraneous solutions. This is not a good example of that because neither of these will be extraneous, but I want to show you what I mean anyways. So the answers, as we claim them to be, are negative 8 and positive 9, right? So if you take the answer negative 8 and you put it here and here, I'm going to start telling you this, check your answers, check your answers. I'm not asking you to check them to see that the left side and the right side equal each other. I'm asking you to check it by putting it in and then make sure that nothing becomes a lawbreaker. If you go back in time quite a ways, at least a week, you'll remember there were some basic expectations or rules of logarithms. And the most commonly broken rule of logarithms is that this stuff in here, do you remember what it's not allowed to be in the yellow jelly bean? Can't be a negative and it can't be a 0, right? So the arguments of a log can never be a negative and it can never be 0. So the rule that's going to get broken, if it's going to get broken, is that when I take an answer, like a candidate, and I put it in, it will make a negative number there. And again, this example may not have been the best time to introduce this because they both will work, but let's give it a shot. If you put negative 8 where the red arrows are, what's the first negative 8? What's negative 8 squared? 64, right? And then 64 minus negative 8 is 64 plus 8, which is 72. So no stress there. And then if I put the other one, remember, was positive 9. And if you put 9 where the green arrows are pointing, what's 9 squared? 81. And what's 81 minus 9? 72. So because we got positive arguments in both of our, uh, when we plugged them in, then we're good to go. So got it? again, I'm not going to go down the road of telling you that you have to physically make sure that this value equals this value. I think that that's a hill that I would like to climb, but my primary focus with you is more let's just look for ones that make obvious bad things bad things happen, right? You guys got it? All right, I'm going to pause this. I'm going to hand out the worksheet and we're going to just start rocking through problems 1 through 6. That's the goal. All right, so we are going to do some problems on assignment number 43 together. So let us start with, so this is assignment number 43, and we'll just go ahead and start with problem 1. And I'm going to copy them onto the board. I know you guys have them in front of you, but because I'm recording, I thought it might be more beneficial to have the problems on the recording. So bear with me, okay? So the first problem says we have the natural log of 3 minus the natural log of, and notice my computer does not put 4x in parentheses. I always will, but this program doesn't, and I can't really control that. So if I'm really ahead of things, I can draw in the parentheses before I photocopy, but that wasn't today. So a couple instances where there are some parentheses that I think should be there, but no big deal. All right. So again, we want to water cycle this, but we cannot. The water cycle does not apply if there's 2 logs on the same side. This converting logarithmic to exponential is very picky. It's very finicky. You need a single log equal to something. There can't be loose pieces and loose ends. And so we're going to take the 2 logarithms on the left, and we're going to do we're going to put into practice what we learned today, and that is let's turn 2 logs into 1. So what will the logarithm on the left say? Now that has been accomplished, it is time to hit it with the water cycle. And for someone who's maybe been out a while, or I don't know, maybe we're all rusty over the weekend. What's the base of the log? It is not in this case. Remember that it is a base 10 if it's an log log. That is a base 10. What is it when it's a natural log, ln? It is e. So I'm going to write this down for you, but I'm going to tend not to probably do this beyond this point. But remember that the natural log, another way to write this could have been the log base e of 3 over 4x equals 1. And if you want to continue to write your natural logs as log base e's for the foreseeable future, you go ahead, okay? Just know that I'm probably not going to. So now that we actually see the base, we can water cycle it up and hit it the same way we always have, and that is to say base to the logarithm equals argument. Like that cycle's never going to veer from that course. And so when we write this exponentially, it's going to be e to the power of 1 equals 3 over 4x. And of course, note that I opted not to write e to the power of 1. That would just be a little weird. So now that we have left the land of logarithmic equations, we can now start the process of solving. We can start having conversations about adding things to both sides and multiplying and dividing and all the things we would have wanted to do. And in this case, we should just kind of instinctively know that this fraction has to take a dirt nap. Like that's just thought number 1 is really regardless of anything else that in my plan of attack entails, I know that I do not want a fraction in my equation. So I'm going to multiply by whatever the bottom of the fraction is, in this case, 4x. And the 4x's on the right-hand side are going to go bye-bye, just like this, like I'm vandalizing. And I'm going to be left with the equation that says 4x e equals 3, right? And remember, the E is not a letter. I know that if we talk about the English alphabet, yes, it's the 5th letter of our alphabet. But in mathematics, E is the number, kind of like pi, 2.71828, so on and so forth. That is just a naturally occurring irrational number. So E is a number. If I want to solve for X, that means I got to get rid of the 4 and the E. How am I going to make them go poof? Divide both sides by 4 and E. Right? Like there's 2 things multiplied onto my target variable. I just very meticulously divide them, pry them both off. And when I divide both sides by 4e, I am left with my answer, which is x equals 3 over 4e. Done. If someone wanted a decimalized version of that answer, they could ask, all right? If someone doesn't specify, someone being like whoever writes math tests, they want exact. And this is exact. The moment you type it in a calculator and e goes in as 2.7 something, and so we wind up with a decimal, the moment you do that, the answer is kind of ruined for exact purposes. But again, someone might want a decimalized approximation, but don't cross that bridge unless you're asked. Leave everything perfect and pure. All right, let's head on to problem 2. In problem number 2, we are given a log base 6 of 9 plus another log base 6 of the quantity x squared plus 3, and that's going to be equal to 2. What's step 1? Yeah. Condense. That's just going to kind of become the word you probably want to use. Condense, right? Condense the logs. So we're taking 2, condensing them into 1. And because it's addition, what are we going to condense using? Multiplication. So we're going to condense these 2 logs into another single log with a base of 6. And what's the argument of the log going to be? 9x squared plus 27. Yeah. I hope you see the value in that step. Like that's a really powerful thing to be able to do. To condense 2 logs into 1 then brings the water cycle into play. And it's the water cycle that really enables us to then use conventional algebra, things like square rooting and multiplying and dividing, like all the skills you should have acquired over the years. But you got to get the logs out of the way, which is what the water cycle does. It's beautiful. So we're going to cycle this thing up and out, and it's going to be this to the power of this, which is 36. And then it equals this. So we can say 36 is equal to 9x squared plus 27. And again, once we get here, then the equation is now solvable. All the stuff that we've worked so hard together, yourself and myself, to learn just how to do algebra. Now we go, oh, I got this. The first thing I'm going to do is because this is not a quadratic like that last one from our notes. This is a quadratic, yes, but it's missing its middle term. So the best approach for a quadratic like this is to get this 27 and move it over there. So we're going to leave the 9x squared here. And what is 36 minus 27? It is 9. And when you divide both sides of this equation by 9, x squared then equals, and there are 2 solutions to this equation. What are they? Correct. Positive or negative 1. Remember that with square rooting in an equation, you always insert the positive negative sign. We saw that with like completing the square. The moment you square root, in pops the positive negative sign. So those are our 2 answers. And now it's important that we go back, and I didn't do this in the last problem, but I'll discuss it with you in a second, but it obviously would have been just fine. If I take my answers positive 1 and negative 1, and I plug them back into the original problem, you don't need to plug them into here because there's no x there. Like, duh. You have to have an input to be able to mess something up. And so if I take, let's start with like negative 1. So one of our answers we claim is x equals negative 1. If you put negative 1 right there, what is negative 1 squared? And 1 plus 3 is 4. So negative 1 passes the test, right? And then if you put the other answer, which we claim is positive 1, right there, you're going to get the same thing, right? 1 squared is 1, 1 plus 3 is 4. So all's well. So both of those answers can stay. That will not be the case throughout this entire assignment. You'll find yourself crossing off answers from time to time. Good so far? Bless you. Bless you times at least 3, but I think maybe 4. You're welcome. Open parenthesis, bless you, close parenthesis to the power of 4. Problem number 3 has us doing a log with a base of 7 of 9 minus a log with a base of 7 of the quantity x minus 7 equals 1. What are we going to do first? Condense, condense, condense. And what is it going to condense into? Log base 7 of what? 9 over x minus 7, right? We're going to condense into a division problem because subtraction condenses to division, right? And we find ourselves again in a situation here where we don't really, I think we saw this like in problem 1 where, we're going to water cycle something up to the power of 1. So really what's the point? So this can just be written as 7 equals 9 over x minus 7. Again, we just don't want to ask a lot of questions about what should I or shouldn't I. The answer is yes. If there's a fraction, should I? Yes. Should I? Yes. I mean, like always kill your fractions. And so in a case like this x minus 7, it can't continue to exist in this problem. So before we really move on, we need to put some monster brackets on and multiply this whole equation by x minus 7. That's just a non-negotiable. Whatever it says on the bottom, you multiply by that, all of it. And these x minus 7s are going to go bye-bye, leaving us with what on the left side? What are we going to get over here on the left? You have to take 7 times x minus 7. Nope. So yes, we started to hear it there. Good job. If you have x minus 7 times 7, all you guys have to do, and I know it's sometimes we just forget things, but that's just distribution, guys and gals. So if you take 7 and distribute it through, you just get 7x minus 49. And then on the right side, of course, we just have 9 because we pulled the bottom out of that fraction. It just dropped down. And it's a pretty instantaneous transformation. Like it goes from looking pretty high schooly to like, yeah, add 49, divide by 7. What's 9 plus 49? Yeah, so we get 7x equals 58. Divide both sides by 7, and we get x equals 58 sevenths. And I want to say that that's it, but really, what would I be forgetting? It's already reduced. Plug it back in. Right. And that's just something you're going to have to train into yourself because you can still probably get, like when our quiz comes up on this in a week or so, you can still probably get maybe a B if you do everything perfect but forget to check your answers, because there's going to be answers that where if you don't check them, you're going to essentially be wrong. So what I want to do at this point is I want to think of 58 sevenths as what it actually is. And you should know that 7 goes into 58 8 times. So if I said I want to know what this kind of sort of is equal to, I would say, well, it's about 8 point something. You might wonder, well, why do I want to know? Well, I'll show you why I want to know, because if I just know that the value of x is 8 and change, take a look at what happens if we go back to the very beginning of the problem. And I mean the very beginning of the problem. I would like to draw your attention to this. Notice I don't care about the other log y. There's no x. And I don't obviously care about this. I care about any logarithm that has a variable in its argument because it has potential to go south. So if I put 8 point something in place of x, what will the result be for this? Positive, right? And that's all I need to know. So he passes the test, so I can take my answer of 58 sevenths and say, I've vetted you, and I can put you in a box. Like I'm committed to that answer. I checked it, it works. We've seen this before with it's been a long time, lots of months, where like putting an answer in a box is like our way of saying, I've checked it, it's good. Right. And if it's not good, then we just cross it out. On we go to problem number 4. Problem number 4 has a log with a base of 2, argument quantity x plus 9, plus a log base 2 of just regular old x equals log with a base of 2. of 22. Sorry, not sorry, but I have to keep asking this question. What do we do first? Condense, condense, condense. I'm going to take the two logs on the left, condense them using what operation? Multiplication. Good job. So we're going to condense it into a single log with a base of 2. And the argument of that log is going to be what? That is just, this purple thing right here is just the result of multiplying these two purple things in case you're starting to get drowsy. So that's all that is. And then the right side is unmodified. It is what it is. It's just log base 2 of 22. What's the next thing we have to do? Good job. The answer prior to this point in the lesson would have been hit it with the water cycle. But as we learned at the tail end of those early notes today, that's not always the appropriate thing. If you have a matching log, log base 2 on the left, log base 2 on the right, just drop the logs. And what pops out is now just the arguments. So I say, well, then x squared plus 9x, I don't know what you are, but you must equal 22 because the arguments have to be the same. And it's sort of interesting, like sometimes when you drop the log and you come out and you look at what you have a little sixth grade equation. And again, this is not that. This is more difficult than that. So we go back to our instincts about quadratic equations and we say, let's pull all the stuff to one side. X squared plus 9x minus 22 equals 0. And then of course we have to factor. I always try to remind my Algebra 1 students about how much harder Algebra 2 is if you are no good at factoring. So since we're coming up soon in Algebra 1 on the factoring unit, I'll have to remember to tell them, like, let's get good at this, okay? So we're going to factor this into x plus 11 times x minus 2, because that's what works. And then what are the solutions? Good. So we have x equals negative 11 and x equals positive 2. And I'm not going to put those into boxes yet, just because I'm not really sure that I want to commit to them just yet. So what I'm going to do is I'm going to grab them, just since I'm teaching you this, and I'm going to pull them back up to the top, and we are going to focus only on the original problem. You'll notice in the original problem that there are two logarithms that contain variables, and they are the surviving things on the television there. So what we want to do is one at a time, we want to take the numbers and plug them in. If I take the number negative 11 and I put it right there, or right there, your log doesn't work. It's an interesting way to say that. Like it's undefined, isn't it? If I put negative 11 in the first one, negative 11 plus 9 is negative 2. And you can't have a log whose argument is negative 2. So we can take the answer negative 11 and hit it with a cross out like this. But that doesn't mean the other one works. Like sometimes they both work, sometimes they both don't, sometimes one works. Like you just are committed to the process of saying check them all, check them both. So let's take the number 2 and put him in. If you put 2 right there where the green arrow is, 2 plus 9 is no worries. And then over here, if you put 2 right here, we're good. Oh, you would say x equals 2. Got it? So again, I want to say, I know I say the same things a lot, but I understand you guys kind of fade in and out of consciousness and you think of other things. You are not checking your answers in the conventional way where we say, does the left side equal the right side? We're just checking to see if anyone causes a law to be broken, which 11, negative 11 did, 2 did not. So x equals 2 can have a box. Negative 11 got a cross out. Still with me? Let's do 5 and 6. 6 is definitely the hardest problem on the entire paper, so I would be really thrilled if we could get to that. So let's knock out 5 pretty quick. 5 should not be difficult for us at all. So 5 has us doing a log base 4 of 8 minus a log base 4 of the quantity x plus 9, and that equals 1. So step 1 is to condense, of course. So the left side is going to condense into a division or a fraction, right? And what's it going to be? Log base 4 of what? And then when we hit it with the water cycle, because there's no logs to drop here, then we're third time today, we're faced with something to the power of one, which is really kind of like pointless. So 4 raised up to the power of 1 is just 4. So we say 4 equals 8 over x plus 9. And then without thinking, what do? Yeah, we're like, we should just be fraction killing robots. Like the step like what we're doing right now isn't up for like a lot of discussion or debate. It's just C fraction, kill fraction. So we're going to multiply both sides by x plus 9. Right. Good job, Coop. So the x plus 9s cancel. And I know that there was some silence on the last one. I would love it if more than just Cooper's one voice could be heard here. What is the left side going to equal? Thank you for saying that. I appreciate that. 4x plus 36, right? You got to distribute in a case like this. And then you divide, or excuse me, subtract 36 from both sides, which gives you 4x equals negative 28. And you get this, and this is an important discussion. Is x allowed to be negative? Yeah, he is. And you don't twist words here. What is not allowed to be negative is the argument of a log. X can be whatever it wants. So what I have to do now is check -7. I'm not interested in whether he's positive or negative. I'm interested in what does he make happen. So I'm going to take the number -7 and I'm going to plug it back up. Always go back to the very beginning of the problem. And the log that I'm interested in is the one in the big yellow box, this one. Nothing else in the problem concerns me at all. So if I take my answer, which is negative, and I put it right here where this arrow is pointing, what is -7 plus 9? We're good. He passed our test, so we can put a box around him and say, you have been vetted, you, sir, may proceed through the gate. And that leaves us with number 6. And then obviously tomorrow will be a work day. I'm saying this on the recording. If anyone ever watches this, they won't care. But Wednesday is the state math contest. And so I don't think anyone else you're doing it. And Brenna, 2 of you. God, I said, well, how inconsiderate of me. That's a day when the 3 of us will be gone. You'll have Mrs. Lloyd here as a sub. So you're going to have quite a few work days coming up, at least the next couple. And I expect you guys just to work. Got it? But there'll be another assignment just like this tomorrow called, wait for it, assignment number 44. And then I might even make a number 45 just to make sure that you're nice and loaded up with work until the end of the day. All right, let's get to it. Problem 6, super fun. And by super fun, I mean, if this were Boston, they'd say this problem's wicked hard. So let's get to it. We have the natural log, and I am going to skip a step just because the clock is telling me that I should. So it is number 6, and if I condense the left-hand side, it's going to say the natural log of x over x plus 6. What's the matter, Coop? Good there? I didn't skip too much, right? I just did the condensing rather than copy the original problem down. That's time to hit it with the old water cycle. What's that going to say? Squared. Good job, guys. E squared equals x over x plus 6. And that was a big jump for me as the guy who does this for a living. Like I didn't show you the E that time. It was your job to know that it was there, log base E. So there we are. We have left the land of logarithms and enter, thank goodness, the land of normal exponential algebra sort of equations, which we have the power to do. We can manipulate stuff by this point. Multiply, move stuff, root stuff, divide stuff, don't care. So without thinking about it, I am going to multiply because I know that there's a fraction and I can't have that. So I'm going to multiply both sides by x plus 6. This is a very uncomfortable math problem for most people. So what is the left side going to say? It's going to be e squared x plus what? Plus 6e squared equals x. Nothing is wrong, but I would venture this is a good time to say, Houston, we have a problem because I'm asking you to solve, of course, for x, right? And the trouble with x is he's in 2 different places. And we learned this in Algebra 1. So Again, for some of us, it might be fresher. But in a case like this, if the variable you're trying to solve for is in multiple positions, there's a massively powerful strategy to fix this problem. And what you do is you take your terms that have your target variable and you bring them onto the same side of the equal sign, and then you factor it out like a GCF. I love this trick. It's so empowering mathematically. So what I'm going to do is I'm going to take the term that I'm going to circle in green, and I'm going to move it over there with its homie because X guy wants to go with other X guy for reasons, again, that you'll soon see. So we're going to have 6e squared equals x minus e squared x. And the reason I'm doing this is because now that my x's are on the same side right here, like here and here, you would agree that x is a common factor of those two terms. You have to take x and you have to essentially undistribute it. You have to pull it out of both terms like this. And if you pull out x, what's left behind? What's left of this term if you pull out x? Very important something. 1. Good. And what's left of the second term if you pull out his x? And you don't have to be a math nerd to appreciate on some level how amazingly powerful that is. That move enables us to take an X that's like trying to divert us, like I'm over here, I'm over here, I'm over here, and we capture him and pull him into one place, and it's like, yeah, the game's over now. Like I got you. And so at this point, if I want to get X by himself, he's in just one place, and all I have to do now is divide both sides by 1 minus e squared. And I'm left with my final answer, which is, well, x equals 6e squared over 1 minus e squared. And you would be inclined, if you're a normal person, which you are, to say, can't I cancel out those e squareds? And the answer is no. That bottom e squared is part of a subtraction problem, so he is off limits. Remember, we've talked about this before. So we made it through problems 1 through 6. I'm impressed. The timing was nice. There's not much time left. You're welcome to get ready to leave, or you're welcome to start another problem. Yeah, this is a lot harder to check. This would be a good time to put it into your calculator. And remind me tomorrow, I'll show you where the E button is on all your calculators. And I can show you. I'm going to be gone Wednesday. I'll be here tomorrow.